Guys, welcome back to Online Learning. So in this video, I want to verify the divergence theorem for a vector field f is equals to fxi minus 2yj plus c squared k taken over the region bounded by x squared plus y squared is equals to 4, and the plane is equals to 0 and z equals to 3. Okay, so what do I want to do? I want to verify the divergence theorem. So the divergence theorem says that if we want to find the total flux of this region, in this case this is the equation of a cylinder, I'm going to draw it when I compute my left side. Okay, so it said that in order to find the total flux, what we're going to do, we're going to find the divergence of this vector. Okay, and after that we're going to perform a triple integral. Okay, so I'm starting with the easy side, which is the right hand side. Okay, so we're given a vector field. Okay, so this is our vector field. F is equal to fxi minus 2y squared j plus z squared k, and I want to find the divergence of this vector field. So I'm going to say divergence of the vector field f is going to be partial. Okay, we're going to take the partial derivative of I, the a component with respect to x, the j component with respect to y, and the z component, the k component with respect to z. Okay, by the way, we're not going to put any in it, so we're going to say 4x plus the partial y of negative 2y squared plus partial z of z squared. Okay, and now if we differentiate here with respect to x, we're going to just get 4, and here we're going to get negative 4y, and here we're going to get 2z. Okay, so now want to compute our triple integral. So this is going to be our total flux. Triple integral of v, here we have 4 minus 4y plus 2z dv. Okay, now we have a small job to do. Want to find the limits. Okay, so this is a cylinder, so I think using cylindrical coordinates will save us some times, and it's very easy. So what I'm going to do, this is a circle, and it's a circle of radius 4, of radius 2, since the equation of a circle is in form x squared plus y squared equals r squared. So I'm going to draw this circle here. Okay, so this is the circle. By the way, it is the shadow of this. The shadow of this cylinder is a circle. Okay, so this is the y and this is the x. Okay, so what I'm going to do in cylindrical coordinates, the angle, which is theta, ranges from this. So it's a full circle, so that means theta ranges from 0 to 2 pi. Okay, what about the radius? Okay, so the radius is just 2. Okay, so it ranges from 0 to 2, not from negative 2 to 2. From 0 to 2. The z coordinates don't change in cylindrical coordinates. Okay, so the lower bound of z is very easy to identify, is 0, and the upper bound of z is equal to 3. Okay, then instead of writing x is same as r cos theta, y is same as r sin theta. Okay, then dy dx, we're going to replace dy dx with r dr d theta. Okay, so now I'm going to plug in these limits. So this is 2 pi for the angle theta, 20 for the radius, then 30 for z. And I'm going to say 4 minus, instead of writing 4y, I'm going to write 4r sine theta plus 2z. Okay, so this is z, we're integrating the z first, dy dx, so it's r dr d theta. Okay, so we're going to integrate with respect to z. We're going to treat everything as constant. So this is going to be 2 pi 0 2 0. Okay, so this same is 4z minus 4 r sine theta z plus 2z squared over 2. Our limit is 3 0 r dr d theta. Okay, so I'm going to say lower bound minus upper bound. So I'm going to replace z with 3. Then I'm going to subtract this whole thing by replacing z with 0. Okay, so if I do that, if 2 pi 0 2 0. Okay, so I'm going to get 12 here. So if you put 0 here, everything go to 0. So I'm going to have 12 4 times 3 minus, I'm going to have 12 again, 12 r sine theta, and here 2 into 2, as you can see, 2 into 2, I'm going to get 1, then plus 3 squared, which is 9, and we have r to theta. By the way, don't forget this r. Okay, and now we want to integrate this, but before integrating this, I think you can just expand, since we have r here. So we're going to have 2 pi 0 2 0. So this is 12 r 12 times r minus 12 r squared sine theta plus 9 r dr d theta. Okay, so this is what we're going to integrate. So I want to integrate here. Okay, so what we're going to just do, we're going to add 1. We're integrating with respect to r. We're going to treat theta as a constant. So you just add the power and divide by the new power. So I'm going to get the integral of 2 0. Okay, so here's 12 r squared over 2. 12 r squared over 2. Then here minus 12 r to the power 3 over 3 sine theta, and here I'm going to just have plus 9r squared over 2. Okay, then we have the limits of r from 2 to 0. Okay, then we have the theta. By the way, could have just add 12r plus 9r. I think that was the short method. Okay, so now I want to integrate here. Let's just clear this up. Okay, so here 2 into 2 1 2 into 12, we're going to get 6. Okay, here 3 into 3 1 3 into 12, we're going to get 4. Okay, so we're going to have a single integral of, so 2 times 2 is 4 times 6, so that is 24, minus 2 times 2 times 2, that is 8, times 4, so we're going to have 32 sine theta. Okay, so here 2 times 2 is 4, divided by 2, that is 2, plus 9. Okay, so we're going to have 2 times 9, that is plus 18 the theta. Okay, and now if we say 24 plus 18, we're going to get 42. So if we integrate here with respect to theta, okay, we're going to get 24 theta. So if we integrate sine theta, we're going to get negative cos theta. Okay, I've gotten 32, and I'm going to multiply this by 32, and you're just going to get 18 theta. Okay, 18 theta. Then our limits from 0 to 2 pi. Okay, so fed 24 plus 18, that is equal to 42 theta, and you are going to have plus cos plus 32. Okay, cos theta times 32. Okay, our limits from 0 to 2 pi. Okay, so you should know that cos theta is, cos 2 pi is equal to 1, and cos 0 is equal to 1. So if you say lower bound, upper bound minus lower bound, you're going to get 42 times 2 pi. Okay, so this is equal to 84 pi. Okay, so the total flux is equal to 84 pi. by the way, if say upper bound minus lower bound, this is going to cancel out, and I'm going to be just left with 42. Okay, so now we're going to the other side. Okay, so we want to compute the flux for each surface. Okay, so the first thing we're going to do, I'm going to draw the surface here, and after that we compute our surface integral. Okay, so I have drawn the cylinder here. Okay, and since z is missing, that means the cylinder lies on the z axis. Okay, so what is very important here is to know how many surfaces do we have. Okay, so we have the bottom surface, which is a circle. Okay, that is surface number 1, and we have this cylindrical surface. Okay, the cylindrical surface, that is surface number 2, and we have the top surface, that is surface number 3. Okay, so what we're going to do, we're going to find the flux here, the flux here, and the flux here. Okay, and we add the total flux, and we should get 84 pi. So that is what we mean when we say verify divergence theorem. We want to get the same answer. Okay, so you should be able to draw. I think if we just sketch this region, this cylinder, I think it will be easy for you. Okay, it will be easy. Okay, so first of all, remember we've discussed about our limits. Okay, so I'm not going to talk about limits anymore. Okay, so these are the limits from 0 to pi for theta. The radius is 2, then z from 0 to 3. Okay, and I'm going to use polar coordinates or cylindrical coordinates. Okay, so here for the surface, I'm going to say the bottom part. Okay, so the surface, I'm going to say the total surface total. I'm going to say surface number 1, this is the bottom, plus surface number 2 plus surface number 3. Okay, so the total flux of this surface is going to be the flux at the bottom surface plus the flux at the surface, the second surface, which is cylindrical surface, plus the flux at the top of this cylinder. Okay, so let me, in order so that I won't get confused, so for the surface number 1, okay, let me just write bottom surface. Bottom surface. Okay, what do we know from the bottom surface? We know that we have this equation, x squared plus y squared is equals to 4. This is the circle. Okay, then what else? Z is equal to 0 in this bottom. Okay, we know that. And for the surface number 2, I'm going to say cylindrical surface. Okay, cylindrical surface. Okay, what is the equation? Okay, so the equation of this cylindrical surface is x squared plus y squared is equals to 4, but z, now z is not constant. Z ranges from 0 up to this point, which is 3. Okay, then for the top surface, surface number 3, I'm going to say the top surface, okay, with the equation of a circle, x squared plus y squared is equals to 4, and z is just equal to 3. Okay, then the other thing, okay, this one is very tricky, is to know the normal. Okay, so what I'm going to do here, I'm going to start with the bottom surface. It's very easy, it's a circle. Then I'm going to the third surface, but it's a circle, and I'll end with this one. This one is a little hard. Okay, so I want to start with the easy things first so that I don't get exhausted. Okay, so now this is what I've listed here, and we're going to add the total flux of this surface, this surface, and this surface. Okay, so remember our formula, we said the total flux is equals to the double integral of f ds. Okay, and you know what is ds. Okay, let me write here. ds is equal to the normal, okay, times a small ds. Okay, so this is what we're going to do. Okay, so first of all, I'm going to start with the bottom surface. Okay. So we said for the bottom surface, we're going to have a double integral of f ds. Okay, and our vector field, okay, let me just write our vector field here. F is equal to 4xi minus 2y squared j plus z squared k. Okay, so we're at the bottom. Okay, so we're at the bottom here. Okay, so the downward normal at the bottom here, so this is a surface. Okay, so the downward normal is in this direction. Okay, so since this is positive c and assuming this thing is oriented upwards, okay, so the downward normal, since this is positive z, so the downward normal is going to be negative z. So in vector form, the normal, okay, for s1, so I'm going to say the normal is equal to negative k. Okay, the downward normal. Okay, so what we're going to do here, I'm going to put my limits. Okay, so double integral 0 to 2 pi for the angle, for the radius 0 to 2, then this vector fxi minus 2y squared j plus z squared k times normal. What is the normal? We say the normal is negative k. Okay, so it's a dot product here. Instead of saying dy dx, I'm going to say r dr d theta. Okay, so if we multiply this vector by this vector, so we should know this is negative k. It's same as saying 0 0 negative 1. Okay, so I'm going to just get 2 pi 0. I'm going to get 0 to 2. So if I multiply, I'm going to just get z squared r dr d theta. Okay, and what is z at the bottom? And our very large z is equals to 0. So I'm going to get 2 pi 0 2 0 0 r dr d theta. Okay, so having a 0 here is not the same like not having a 0 here. So if we don't have anything here, that means we have 1. But if we have 0, automatically we're going to get 0. Okay, so if we integrate 0 with respect to r, we're going to get 0r. Okay, so it's just a 0. Okay, this was for the surface, the bottom surface. Okay, for the meantime, I'm going to the third surface, which is easier. So for third surface, what is the normal? Okay, so we have the upward normal in this direction. Okay, in this upward normal, z is increasing, so that means the normal for surface number 2, okay, so the normal is positive k. So I'm just going to have a double integral 2 pi 0 2 0. I'm going to multiply this vector 4xi minus 2y squared j plus z squared k negative k. It's now positive k. Okay, r dr d theta. Okay, and we have said that this is same as saying 0i 0j plus 1k. Okay, so we're going to have 2 pi 0 2 0, and if we multiply here, we're going to get z squared r dr d theta, and the z here is not equal to 0, z is equal to 3. Okay, so we're going to have 2 pi 0 2 0 3 squared, that is 9, times r. We're going to have 9r dr d theta, and we're going to integrate with respect to r, so we're going to have 2 pi 0 9 r squared over 2. Our limits from 0 to 2 d theta. Okay, and if we do it, what we're going to get, 2 times 2 we get divided by 2, so this is same as saying 0 to 2 pi, so we're going to have 18 d theta. Okay, and if we integrate respect to theta, we're going to have 18 theta the angle from 0 to 2 pi. So this same is saying 36 pi. That was for the third surface. Okay, I'm sorry, the second surface, the third surface. Okay, so now I finished with the easier surface, the first one and the third. Now I'm going to the second surface. Okay, so for the second surface, the reason why it is hard, we don't know the normal. Okay, so the normal is neither positive k or negative k. Okay, so for this surface, okay, so now the outward flux can be anywhere in this direction, okay, or in this direction, or out of the page and into the page. Okay, so we don't know, it's not either negative k or positive k, but it can be either x, y, or x component plus y component. So what we're going to do, we don't want to stress ourselves. What if we just say let the normal be equal to cos theta I plus sine theta j? Okay, and if we, okay, the other thing right now, okay, the other thing we're concerned about, we're no longer concerned about the radius. Okay, so we're now concerned about this distance from here to here. Okay, so that means we need z in our integral. Okay, and we are concerned about this circular, so we are now concerned about the angle, which is now 2 pi. Okay, so the radius in this case doesn't matter. Okay, what only matters is the height from this point to this point and the angle. Okay, because we're going to rotate, or rotating outside on the cylindrical surface. Okay, so now what we're going to do, our double integral, we have, okay, the angle from 0 to 2 pi. Okay, and this distance z0 to z3. Okay, so from 0 to 3, but we're using cylindrical coordinates. Okay, so that means we're not going to forget our Jacobian. Okay, so here I'm going to say times what was the vector field. It's 4xi minus 2y squared j plus z squared k. Okay, times the normal, we said cos theta I plus sine theta j. So we get, that means our normal depends on the angle. Okay, then we have r d theta. Okay, but I said we're no longer concerned about r, so instead of writing the r, I'm going to say dz d theta. Okay, so when you say the r d theta, we're saying r is the radius. So in this case, z is not the radius. That's what I'm trying to say, in other words. Okay, and if we perform this double integral, okay, so what we're going to get, we have 2 pi. Okay, by the way, we don't have r here, but we know the radius of the circle is equal to 2. Okay, so we're going to have 2 pi 0 3 0. Okay, so we're going to have 4x cos theta, 4x cos theta, negative 2y squared sine theta. Okay, plus 0. You don't have any k component there, so it's plus 0. Okay, times r, we said r is equal to 2, which is the radius. So I'm going to have 2 dz d theta. Okay, and okay, let's simplify here. 0 0 3 0. Okay, we know that x in cylindrical coordinates is equal to r cos theta. Okay, so I'm going to say 4, and for x, r is 2 cos theta times this cos theta. Okay, minus 2, we know y equals to r sine theta, so I'm going to say 2 squared sine theta squared times this sine theta. Okay, but we have this 2. Okay, so dz d theta. Okay, 2 pi 0 30. So here are going to have 8 cos squared theta, and they are going to have minus 8 sine cubed theta. Okay, and we're going to multiply this by 2 dz d theta 2 pi 0 to 3, because of this 16 cos squared theta minus 16 sine cubed theta dz d theta. I think now I can integrate this back to z. Okay, so it's from 2 pi 0. Okay, so we're going to have 16z cos squared theta minus 16z sine cubed theta. Our limit is 3 to 0 d theta. Okay, so if we say 16 times 3, that is equal to 48. So we're going to have 48 cos squared theta minus 48 sine cubed theta d theta. And now I want to integrate with respect to theta. Okay, so cos, we're going to, instead of writing cos squared theta, we're going to write cos squared theta as 2 cos, sorry, we're going to write cos theta as cos 2 theta over 2 minus 1/2. We're using the double angle formula. Okay, and if you're in an exam in a hurry, just know if you integrate sine cubed theta of a region from 0 to 2 pi, you're going to get 0. But I'm just going to do it so that some of you may want to know why I'm going to integrate sine cubed theta. Okay, but just know this is equal to 0, but cos squared theta is not equal to 0. Okay, so now I've said, okay, I think let me just write all the identities here. In other words, I'm just saying cos 2 theta is equal to 1 minus 2 sine squared theta, 2 cos squared theta minus 1, okay, or cos squared theta minus sine squared theta. Okay, so yeah, just want to make cos squared theta such with the formula. And to make cos squared theta such with the formula, what are we going to do? We're going to add 1 to this side and divide it by 2. So that means we have a positive here. Okay, so we're just saying if we make cos squared theta such with the formula here, we're going to get cos 2 theta over 2 plus 1/2 d theta. And here I just split my integrals. Okay, so I have, instead of writing sine cubed theta, I've write sine squared theta times sine theta. Okay, this is going to ease my substitution. Okay, so what I'm going to do here, I'm going to finish my integrals here. Said we got 48 0 to 2 pi of cos 2 theta over 2 plus 1/2 theta minus 48 0 to 2 pi. Okay, so look, we have sine squared theta. So I'm going to write sine squared theta is 1 minus cos squared theta all times sine theta d theta. Okay, and now let's integrate respect to theta here. If integrate respect to theta, we're going to give 48, okay, negative sine 2 theta over 2, but we have to multiply by the derivative of the angle, which is 2 plus 1/2 theta. Okay, I'm sorry, I just read the theta should not be there. Okay, minus, we have our limits, we have to put our limits. Okay, from 0 to 2 pi. Okay, minus 48 0 to 2 pi. I'm not going to expand here, I'm going to leave it like t is cos theta. Okay, sine theta d theta. If we say upper bound minus lower bound, you should remember that sine 2 pi equals to 0, so sine 4 pi is equals to 0. then sine 0 is equal to 0. So I'm going to have 48 0 plus 1/2 times 2 pi, okay, and this is equal to 48 pi, okay. And we said for this part, okay, so here we have negative 48 0 to 2 pi of 1 minus cos squared theta sine theta d theta. Okay, so I'm going to use u substitution. So I'm going to say let u, I'm right here, let u be equal to cos theta du d theta is going to negative sine theta, and if we make the theta substitute the formula, we're going to say du over negative sine theta. So that means I'm not going to change the limits. Negative 48 0 to 2 pi 1 minus u squared, okay, times sine theta, and for du I'm going to say, for the theta I'm going to say du negative sine theta. Okay, so as you can see, this will cancel this, okay, and now I'm going to say negative 48 0 to 2 pi of negative and negative, so that means I have a positive here, 1 minus u squared du, okay, and if we integrate back to u, going to have 48 u minus u to the power 3 over 3 0 to 2 pi, okay, and you remember that u is equal to cos theta, so the same as saying 48 cos theta minus cos cubed theta over 3 from 0 to 2 pi, and we said cos 2 pi is equal to 1, cos 0 is also 1, so say 1 minus 1 we're going to get 0. So that means the total flux is going to be, we say the total flux for the surface, okay, flux is going to be, the flux is surface 1, flux is surface 2, and flux is surface 3, okay. So for the first surface we get 0, for second surface we have 48 pi, and for the third surface we have 36 pi, and if we say 36 plus 48, that is equal to 84 pi, okay. So what does that mean? We know that when we use divergence theorem we also have 45 pi, so our conclusion is that f ds is equal to the triple integral of the divergence of the vector field dv. So we have verified the divergence theorem. Thanks for watching. For your likes and comments, okay. So if you have any questions, you can just let me know in the comment section, okay. So in my next video I'll show you what if you don't know the normal, yeah, how you can calculate the normal, okay. So yeah, I was just saying the normal is negative k, some of you may not getting that, okay. So in the next video I'm going to show you, let's say I don't know what is the formula of finding the normal, okay. Thank you.